Good morning. How are you? Welcome to the Table Talk with Bob Colbert. I'm your host, Bob Colbert. Today we will be discussing artificial intelligence. So, a little bit about my background. I worked for Lockheed Martin and I worked some special operation forces type projects. One of those being artificial intelligence app development. So do have some experience on this. So what I'm going to do is kind of give a high level artificial intelligence introductory material, maybe at a high school level. So hope you just sit back and enjoy, get you a soda or coffee, and I promise I won't put you to sleep. So anywho, all right, let's get started. By the way, before we're getting on 12/9/23, so we're getting really close to Christmas, so it's about time to do your Christmas shopping, so y'all get to it. All right, well, let's get on it. So I'm going to start with some videos first. So before I start the video, let me give some background. So back in episode 4, we discussed the SAG-AFTRA strike. What that was a strike of Hollywood actors and producers. And the two main issues that were besetting the two parties there were, one, streaming revenues. Traditionally, broadcast television or cable television type programs had their own kind of revenue stream development, and streaming of shows is kind of a different animal, I guess. And so the revenues were apparently less that would be garnered or gained by the actors. So that was a big issue, to make sure that there was parity of revenue streams between the various income streams. The other major issues was artificial intelligence. The concern there is actors not being able to control their likeness with artificial intelligence app, whether it be from images or even potential video development. And so that was a big issue. So the position was that the actors wanted control of that process to make sure that they had a voice in there. Some people don't mind having their images in artificial intelligence medium. Some do. So you just want to make sure that it's fair among the parties. So if you missed the episode 4, I'll show a video that kind of speaks to what the issue was. And so here we go. Let me go to the full case.
It's the moment actors learn their 118-day-long strike is over. This morning, we were with the Actors Union strike captains as they were still celebrating at breakfast.
I woke up going, I can't believe it. I'm so thrilled.
We fought for and won a historic contract, and AI is not going to take our jobs.
Deborah spoke to SAG-AFTRA president Fran Drescher today about the historic deal.
In a nutshell, what does this new agreement provide to the Actors Union?
Well, it adds a lot more money. We opened up a new stream of revenue for those people that are on the streaming platform, and that was a very big deal.
Equally importantly, you got protections on AI.
Everything requires the consent of the SAG-AFTRA member. That is major.
She also shared her secret weapon during negotiations.
There he is. What's his name and what's his purpose?
Love, without any regret or apologies. I would take this little guy out and I would sit him on the table right opposite Bob Iger. I turned it into a woman and girls movement to lead with empathy, dignity, intellect, to be you.
With the strike finally over, today everyone wants to know how soon will their favorite TV shows return. Variety's Michael Schneider.
The second the strike ended, they could hit the ground running, and that's exactly what's going to be. Studio space has been rented out. Talent is on hold.
He says some shows will return as soon as January.
The first shows you'll see are the traditional broadcast shows. So NCIS, the shows that you normally expect to see 22 episodes a season, they'll be able to salvage half of those seasons this year.
Alrighty. Well, I do credit Inside Edition for that video. That was Fran Esker from the SAG-AFTRA organization. She's the president. And so, as of right now, the membership of the SAG-AFTRA union has voted to ratify that contract. So, all right. So what you're looking at now are neurons in a petri dish. And let me pull it over just a little bit so you can just see it just a hair bit more. And so what you're going to see is you're going to see these neurons establish a connection. And don't worry about what a neuron is. We'll go over that. So look at this, and it's amazing.
What you're looking at here are two neurons under the microscope that I've filmed. And if you wait really patiently, you'll be able to see them connecting to one another.
All right. So what I'll do is I'll go ahead and close that one. Let me see. Oh.
What you're looking at here are two neurons.
And this is a mouse brain of neurons firing, and it's being imaged by folks at UCLA Health. And I credit the David Geffen School of Medicine at UCLA for this. And I credit Dr. Gautam Alabadia for imaging the human brain neurons firing. All right. So I'll go ahead and get rid of those two. All right. So what is artificial intelligence? Well, as you know, we're humans, so we have an organic type of intelligence. Some people might say some are more intelligent than others. But basically, if you're a healthy human being, then you have billions of those neurons firing. They're connected and they're firing. So we'll assume that all humans that are alive and reasonably not compromised have billions of connections of neurons. So what artificial intelligence tries to do is to look at that as a model to emulate. So what artificial intelligence, or AI, is the intelligence of machines, or we're talking about robots, machines, or software. So it doesn't have to be a machine, it could be software as well. I personally develop software apps that are artificial intelligence. And this is opposed to the intelligence of humans or animals. So it is technically a field of study in computer science which develops and studies intelligent machines or software. And such machines or software are typically called AI or AI apps. And AI technologies is now widely used throughout industry. And you just saw the entertainment industry, the movie production studios, trying to come up with some reasonable rules and controls over AI in the entertainment industry. So it affects all industries practically, especially the aerospace industry, government, and much more. So yeah, so I'll go ahead and do that. All right. So currently, and we'll keep it very high level. So AI, what we are now in a time and space and a place where AI is a once in a lifetime commercial and defense and human society game changer. Why do I say that? Because now hundreds of billions of dollars in public and private capital are being currently invested in AI development, machine learning. We have AI companies like NVIDIA that develop AI chips. We've got the social media companies, Facebook, X, Google, Microsoft, all developing AI apps and trying to integrate it into their product set. And they're trying to incorporate machine learning or AI into all of their workflow processes in just about every company. So like Amazon's using robots and AI to do their kind of things. Lockheed's using it to develop aircraft and sensors and apps, and entertainment is looking at using it for supplementing or helping to cut costs down and increase the productivity of making music and television shows. And you can write, writers are looking at when you're writing scripts or novels to help. AI helps to create outlines and help to fill in character development and story development and things like that. So hospitals are using it in their workflow processes. Research organizations are using it to develop new medicines, drugs, and such. So research is using it to find answers to cure diseases, and so it's just everywhere. It's very pervasive. It has to be regulated by the federal government because, right now and in the past, since the 1950s when computers came on the scene and stuff, really AI's been going since then. And what it is a mathematical construct or computer programming kind of a thing. So yeah, so it's been going on for a long time. But why is it all of a sudden just exploded? Well, because computer technology has exploded. What I'm talking about, the number of transistors that are on these IC integrated chips on computers is incredible. I mean, it's in billions and billions of transistors, and we're getting to the point where we're developing petaflops of data that are it's just enormous. So why are we needing this level of memory and transistor calculations capability? Because there are a lot of simulations that need to be developed, like weather phenomenon. How do you model weather on planet Earth or on any planetary body on there? That's a highly nonlinear system. How do you develop drugs in a timely manner? Highly nonlinear. How about trying to unify quantum theory with gravity, and theory of relativity? Cosmology is an extremely computer-intensive endeavor and highly nonlinear as well. So to develop all of these simulations, it needs computers with very fast chips, and the mathematical constructs from, in eons past, it seems, mathematics, since it's been around, were like geometry based, and then we're now moving into rules based and getting into high level of mathematical constructs, rheology, or is what they call it, kind of things that will allow you to simulate the Big Bang, theory, and how the universe started from nothing and into what it is today. So to do all that kind of just takes incredible, intensive computer resources, software, and stuff. So AI proposes a solution to that. So that's why we have it. All right. So when we're talking about artificial intelligence, we're talking about modeling the human brain, and we just saw neurons. And so what we're developing is a artificial neuron called and set it up in a network, and it's called a neural network. So if you were to break it down, a neuron in a human brain or a mouse brain, it's made up of about 1 billion neurons, the human brain, 100 billion neurons. And so this is kind of the basic look of a neuron. So it has a nucleus right here, and you saw that. Then it has these tentacles that are like, if you want to call it like roots or something, that kind of, and they're very flexible, highly flexible, and these are all swimming in like a fluid, so everything's kind of like, it's almost like a creature in the ocean or something, very weird type organization. And these tentacles, they have what they call axon terminals on the end. And so what these do is these axon terminals reach out swimming, you're swimming in this fluid, and it can sense, it has the sensory ability to detect that, hey, there's another dendrite axial terminal near, and they kind of swim toward each other, and then they connect. And then electrical signals then start flowing in there. So there's different types of neurons. And they're kind of dedicated to specialization. One would be like for muscular neurons, where it's controlling muscles. One of them's for senses, sensory, like eyes, ears, nose, smell, the five senses. And then the other neurons, which is most would be like for intelligence and stuff. And all of those 100 billion neurons kind of grows into this tentacle organism, what we call the brain. And so what we're doing is developing artificial neurons, a mathematical construct version of it, so that it too can be connected together in layers. We call them active or inactive layers, hidden layers, all that stuff. And they're all kind of connected by numbers. Okay. And then how do they look? So, these axon terminals, you can see they're kind of touching, and all of these are chemical kind of transmitters, neural transmitters that get deposited into sockets. You see like a little hole there, and these sensor kind of connect into here, kind of like a Lego block, boom, and they connect and make that strong connection. And these little round things are called neurotransmitters. Yep. So you can kind of understand what the similarities are between the brain and an artificial neural network. So the brain has an organic network. We're trying to develop an artificial neural network. So the similarities are neurons. They make connections between other neurons. And then learning is equal to the change of connections, not necessarily the change of the amount of neurons. And so all of this posits the ability to do massive parallel processing in computer simulations, which means that it's a type of computer processing that is used in highly advanced simulations, like predicting the weather patterns, cosmology, the flow of matter and energy in the universe, how things come together, stars, galaxies, and everything. All right. So in an artificial neuron, what we're doing is a much simpler version of the organic, so that computation within an artificial neuron can be vastly simplified. And we can use mathematics, discrete time steps. We can use some form of supervised learning with a massive number of stimuli, basically numbers. All right, so I'll close that out. All right, so neural network motivation. So human brains are the only example of actual intelligence. Now, I'm not saying that whales are not highly intelligent, elephants, or any other creature, but I don't know of any whales or dolphins or elephants that have been able, like humans, to create rockets and aircraft that can go into space, build space stations, go to other planets, try to create understanding, or what you would call observe the universe. Okay, so to understand the universe is you have to observe it. And as far as I know, I don't think whales are developing theories of relativity. So that's why human brains are what we call only known example of actual intelligence. There could be highly intelligent species in other planets, so we're not discounting that. So individual neurons by themselves are slow and boring. They're just receiving and transmitting signals. But when you put them together in some massive, like, organism kind of a thing, or in kind of bring them together then you can use what's called massive parallelism. And so what we're trying to do, and that's exactly what the human brain's doing, is using massive parallelism to control our bodies and our intelligence. So the idea is, just like we do on sonar, and we look to nature, dolphins have and whales have sonar, so submarines have sonar, so we're copying what works. That's the whole point. So all of this high level of computation, ability, and advanced computer chips, it raises many issues. And this is a computational metaphor suited best for computational hardware and computational software development. And so what we're trying to do is to aim for the high and not aim too low. Okay, so we're trying to understand everything there is to know about AI. So if you kind of compare different, between a computer and a brain, this kind of gives you an idea of where we are currently. Oops, sorry. So these are some values or metrics that are important in computers, and we have a similar thing for brains. So the state-of-the-art computers of today have 10 to the 10th power transistors per CPU or computer. That's a lot. But a human brain has 10 to the 11th power neurons per brain. So as far as computational capability, we're still growing and developing to make sure that our computational hardware is matching our brain hardware. And I'll talk about Moore's Law and transistors in a minute. But we're starting to reach the limit of our ability on putting more and more transistors on smaller and smaller IC chips because it's hardware, it's real matter, and they occupy space, and so there's a limit as to how many transistors you can put on a chip. So what do? You develop quantum computers. So that's and that reaches into the quantum world, and so that is the kind of the direction that's being used to increase this metric so that it can match the brain. Now, if you look at storage, we're all familiar with storage, our memory storage. Well, computers, now these are the best of today's computers. 10 to 11 bits RAM, random access memory, and 10 to the 13 bits high definition. So a brain has 10 to the 11 neurons, so that's similar, and brains have 10 to the 14 synapses, which are right here. We're still growing. Now, if you look at cycle time, how long it takes for a calculation to happen, computers are much faster than the brain. And that's why we have computers, because computers can calculate much faster than we can process information. So when I was studying psychology, they were saying that if you were reading a book or magazine or whatever, your brain can only absorb 100 bits per second of information written, but could absorb 1,000,000 bits per second if it were visual communication. So that kind of shows you a difference right there. All right. So the bandwidth, this is how many bits per second are possible. So in the best of today's computers, we got 10 to the 10th power bits per second. Our human brain, this is an individual brain, one brain, 10 to the 14 bits per second. So we're growing, we're getting there. And the computational power, operations per second, and that's calculations per second, 10 to the 10th power calculations or ops per second versus a human brain 10 to the 14 ops per second. Okay, so you can kind of look in a comparison way where we are computer-wise and what our brains have been created to do now and have for a very long time. All right. So I think done that. So what I wanted to do here is show Moore's law. So, all right. So I was talking about transistors on IC chips, integrated chips. And so the number of transistors since early 1970s, let me see if I can pull this down just here. It doesn't look like I can do that. So anyway, since the scale is 1970 to 2010, so about every 2 years, the number of transistors that can go on a chip have doubled. About every 2 years or 1.96 years. So that makes for a rather linear kind of a process. Okay. All right. This is another more detailed, and let me show you what it's showing. So this is Moore's law, and we're talking about transistor counts. So you kind of get an idea. We're looking at 50 billion. Looks like, or is that million? That's 100,000, 50 million, I think. Transistors on a chip. And these are all of the chips that have been that have been developed over the years. And it kind of follows a linear power of doubling every 2 years from about 1971 to 2018. Now, I credit our world in data for this chart. Okay. Now, when it comes to artificial intelligence, the growth is different. Okay, so if you look, I don't know how. Let's see, I can't. I guess this is about the best I can do right there. So we were looking at, these are memory kind of thing. So we were looking at 100,000 flops. It's kind of a unit of measure per, like a perceptron mark built in 1957-58 time frame. That's how long it's been. and that wasn't very much. And then it kind of just slowly grew. There was not much investment, not much progress, but there were some progress. But then all of a sudden, our number of transistors in our computational capabilities were just like multiplying, just getting ridiculous. So if you notice, this is not a linear growth, but it's an exponential growth. So as you can tell today, if you look at the AI systems, these color dots here, like vision, gains, drawing, language models, large language models, other neural networks that have been developed and are just increasing exponentially. And so what that means, if you were to look, let me just kind of blow it up. So it wasn't that long ago we were hearing about AlphaGo beating the world's chess player, and then all of a sudden ChatGPT comes online in 2020, 314 million petaflops. It can produce high quality text that is often indistinguishable from human writing. So we're now Minerva, built in 2022 and trained on 2.7 billion petaflops, can solve complex mathematical problems at the college level. So, and as you can tell, as the years go by, in 2040, it's growing exponentially. So the era of AI is going to go from, and this is DALL-E, by the way, that can develop images from written descriptions or prompts. They call it prompts. All right. So I'm going to do another video. Just listen first. Watch this.
I can't think of anything personally any cooler than trying to use quantum computers to build intelligent machines, so this is very exciting to me. This is what they look like. There are two of them. These are from our lab in Burnaby in British Columbia. From the outside, they look like giant black monoliths. And they are powered, they have a fridge inside them, a refrigerator that cools these chips to almost absolute zero. Hundreds of times colder than interstellar space. Amongst the coldest and most isolated and extreme conditions that humans have ever been able to engineer. At the heart of this big box is a tiny chip about the size of your thumbnail. And on this chip resides all of the wonder and magic that makes this thing go. In a quantum computer, that device can be in this strange situation where these two parallel universes have a nexus, a point in space where they overlap. And when you increase the number of these devices, every time you add one of these qubits, you double the number of these parallel universes that you have access to, until such time when you get to a chip like this, which is about 500 of these bits, you have something like 2 to the 500th power of these guys living in that chip. We've been doing this for some time now, and in fact we have our own version of Moore's Law. The doubling of the number of these qubits on the chip has happened once a year for the past 9 years. So for the last 9 years, every year the number of these qubit devices has doubled, and it will continue to do so. I believe that humanity is on the cusp of the most important technological revolution that's ever occurred. And that I don't mean that they're better calculators. I don't mean that they're better at searching. I mean everything. And I think that we're very close. And my prediction is that within 15 years, we will have machines that outpace humans in everything. Thank you very much.
I credit Jordy Rose of Kendra AI for that. So yeah, you were hearing about qubits and quantum dots and everything. So parallel universes. So when you get down to the quantum mechanics level, basically you've got particles, and I can't really understand how it works myself. I'm still working on it. I like cosmology. I study that. But when you were talking about neuron connections and stuff, where you got a neuron axion connecting to another neuron axion, and it's changing information. Well, in quantum mechanics and quantum superposition, you could have a particle of matter, an atom, that is, let's just say, on Earth, and you could have another particle that's at 13 and a half or 14 billion light years away at the very beginning of the universe, and those two particles can be connected and exchange information. Really? Yeah. That's what we're talking. So, as I said, when it comes to the exponential growth, computing on a logarithmic plot, what we're talking about here, this is where we are today, and let's just say what the x-axis is the number of calculations or operations per second per $1,000 invested. So we're here at 10 to the 16th power of that metric in 2023. We're still just barely above a mouse brain. But 10 to 16 is one human brain. This is one human brain. And you can tell that by 2050, we're going to be at the level of 10 to 26 power, which is all humans in existence. The ability to do that. We're talking about 2050. It's almost 2025. We're talking about 27 years. So we're going to go from a level of one human capability to all humans. The brain power, if you want to call it, all of the neuron power of all people anywhere on the planet in 25 or 27 years is the prediction. So you can imagine as we go on in time, 2100, that AI is going to take over. Yeah. All right. Well, I think I'll call it there and let that kind of sink in. I think that's enough. I'll try to do another one sometime in the future. All right. So today we talked about artificial intelligence and what it is, how it's growing. It's growing exponentially. It's been going on since the early days of computing. And if you'll look at right here, Alan Turing developed a test. He was a very big contributor. John McCarthy is like one of the fathers of AI, Marvin Minsky. And then the popular AI languages of today of building machine learning apps is Python, Java, and R. So if you're interested in AI development, I suggest learning those, especially Python and R. So I'll go ahead and call it. It's getting a little lengthy. We've been going 45 minutes, but I think I'll stop there. I hope you have a great rest of Saturday. I think college football's kind of had all of its conference championship. There was some controversy, obviously, in the teams chosen. So we got Christmas coming up, New Year's, Super Bowl. Yeah, so there's a lot of stuff. So wherever you are, I hope you have a great Saturday. And y'all take care, my friends. Bye.
You do, you into me, but I can't let it go so easily until I see what it could be eternity or just a week. But yeah, our chemistry is off the chain, it's perfect now, but will it change? This ain't a yes, this ain't a no. Just do your thing, we'll see how we go.